Right. So we have seen how to train linear regression. So the idea is that we come up with a so-called loss function, so L of beta. So beta are parameters of our linear regression, and the loss function shows how much the predicted values deviate from observed data, right? So the higher the loss function is, the more is deviation. So loss function is deviation. So we want to find the minimum of minimum value of our loss function. To do this, we calculate partial derivatives of our loss function with respect to beta. So the vector beta has p plus 1 entries, and we equate them to 0. Now, for linear regression, we are able to solve these equations explicitly. But for more complex models, for logistic regression, and in future we will see artificial neural networks, we will not be able to. So the idea is the same, to write down some loss function as a function of parameters and find its minimum value. But for complex models, we are not able to solve this equation explicitly. So we have to do something else. And this something else is called gradient descent, right? So let us look at how gradient descent works. Now, to understand gradient descent, a good idea is to look at some plots, right? So in calculus, you learned that the graph of a function of two variables can be visualized as a surface in the 3D space, right? So, and by just looking at this graph, we can see some local minima here. There are also local maxima, but if you think that this to be like a loss function, then we don't really care much about local maxima. We only care about local minima, right? So these are local minima. So another way to visualize it as a contour plot, right? So so here I plotted it so that darker colors mean lower values, right? So and here we see local minima, right? So these are local. This is a local minimum. This is another local minimum, and so on and so forth, right? So these are local minimum. Now, also recall in calculus you learned what the gradient is. So the gradient of a function is a vector whose entries are partial derivatives of that function, right? So and the gradient vector, it is always perpendicular to level curves, and it points in the direction of the fastest increase of the function. So for example, so this gradient vector, and in let's say at this point, so the gradient vector is going to point in this direction, right? So because it's going to be perpendicular to the level curve, and it's going to show the direction in which the function is increasing, or in this at this point the gradient is going to be pointing here. So at this point the gradient is going to be pointing here, and so on and so forth, right? So which brings us to this method of gradient descent, right? So here is the formal definition of the gradient. So it's a vector. If we have two variables, then it's a two-component vector. So it belongs to R2, and its entries are partial derivatives of our function with respect to the two variables. So it is perpendicular to the level curves, right? So which we have just seen on the picture. And the gradient descent algorithm works like this. Basically, so we should begin at some initial point, right? Well, like I don't know, here. So we find the gradient vector. So let's say this is our gradient, and we make a small step in the direction of this gradient vector. So then we calculate the gradient again. So at this point, it's going to be probably point in a different direction. So we make a small step in that direction, and so on and so forth, right? So this number alpha here, it governs the size of our steps. So it's called a learning rate. So learning rate. In learning rate. So in say in the deep learning literature, you will always see this learning rate. So then I just repeat it, like make a small step in this direction again and again and again. So notice that the negative sign here is because we want to the value of our function to decrease rather than to increase. So which is why we are stepping in the direction of the negative gradient, and so on. So then we either stop after a fixed number of steps, or we stop when we kind of reach a good point. So when the gradient is approximately 0. So remember that the at the minimum point, the gradient is going to be exactly 0. So if we stop when it is approximately equal to 0, this is probably good enough. So here are some illustrations. So what it looks like. So these are level curves of our function, and let me run the gradient descent algorithm. So it looks like movie. So we do step by step, and then eventually we're going to end up at a local minimum here. So if we begin with a different point, then we are going to end up in a different local minimum. So notice that now we are moving towards a different local minimum. And which of them is going to be the global minimum? It's impossible to tell in advance, right? So if our function has a lot of different local minima, then the gradient descent, depending on the initial point, it's going to eventually find one or another, but which one we don't know. So we cannot guarantee that it's going to find the global minimum. Okay, so here is a little quiz for you.